Hello, everyone. So it's time to start now.
Good morning.
Good morning. So everybody can hear me?
Yeah, pretty well.
Okay, then let's start. So before we start, several things about our course. First, don't forget, we will have the midterm on Thursday night. Okay, from Thursday night to Friday night, 7 to 8. Okay, Thursday night, Thursday 7 p.m. to Friday 8 p.m. Okay, don't forget that. And another thing is, well, I'm sorry that today I have to catch a train, so I'm not able to have my office hour today. Sorry about that. And I will still have my office hour tomorrow. And for Thursday, I will also have additional office hour since, well, you may have your final for your ODE course. So, well, my additional office hour will be after class. I will stay there for 2 hours. Okay. And about Thursday's class, well, today what we are going to discuss is some application of what we have learned. Application about group theory, mainly on the Sylow theory, Sylow subgroup theory. This is something I will assume you know. Okay, at least for the Sylow subgroup theory, I will assume you know. And this kind of application, I assume you also be able to do that. Okay, but on Thursday, what I'm going to do is I'm going to do a review, a very brief review, takes about like 30 minutes. And then I will try to tell you how to play with magic cube of order 2 and how you can try to use some idea of the group theory to study how to play it. Okay, and it will take us about another half hour or maybe 40 minutes. And then after that, it will be a Q&A session. Well, and also my office hour, you can bring whatever question to me and ask me, okay? So on Thursday, what we are going to do is 30 minutes for the review and 30 minutes or maybe 40 minutes for the magic cube, just for fun, just to make you kind of relax, okay? Because you are in the final week. By the way, so this time for your final, again, as I mentioned before, 80% of your problems will be based on the group theory and 20% will be based on, well, what you have learned before, okay? And it will be slightly harder than your midterm, okay? It will be slightly harder than midterm. So before we move on, any question? Any question?
Wait, sorry. So our lecture on Thursday is the same time?
It's the same time. It's the same time. It just will be shorter. Yeah. If you do not have any question, then it will be shorter. Otherwise, well, it will still be that long and I'll be there for another 2 hours. Okay. Any other question? Okay, then let's start. Let me introduce more examples about Sylow theory. Remember, what is Sylow theory? What are Sylow theorems? Okay, Sylow theorems, we have 3, and the first one is there exists at least one Sylow P subgroup for any group G. Okay, what is the definition of Sylow P subgroup? Well, Sylow P subgroup means, okay, the highest power of P that divides your group's order, and you take that kind of group of order that P to that order. Okay, this is so-called the Sylow P groups. Well, Sylow 1 just say that, okay, there exists such kind of group. Okay, and Sylow 2 simply tells you all the Sylow subgroup, all the Sylow P subgroup are conjugate to each other. And that simply means as long as you have one, then you are supposed to get all of them. And you may get a lot, but well, they are all conjugate to each other. Okay, so which means you can get all the Sylow P subgroup by the group action, by taking the group action of the whole group G. Okay, and Sylow 3 is well, very interesting one. It just to say that, well, although we don't really know how many Sylow subgroup we have, but we are able to estimate how many. Okay, we have some criteria to check how many Sylow subgroup you have. Okay, of G, and then S divided by G plus S mod P equals to 1. Okay, so it gives us some criteria to check what kind of possible value of S you could have. Okay, and we've seen some examples last time to see, okay, Sylow theorems are really useful because it can tell us a lot of things. It can tell us about classification of a finite group, well, at least for some very small finite groups. Okay, and today, before we do very concrete examples, let's try to warm up and prove something by Sylow theorems and prove this kind of abstract theorems. Okay, we are not going to use the theorems, we just use them as an application of Sylow's group theory. Okay, this is another example. It's a theorem. Theorems is getting by a mathematician called Frontini. Okay, Frontini theory. It says that, okay, again, suppose the G's order is equals to n times p to the power r, and the GCD of n p equals to 1. Okay, now suppose you have a normal subgroup n, and p is a Sylow p subgroup of n. So which means, okay, p is a subgroup of n. Okay, it's very small. Okay, it's very small. It's smaller than m. M is kind of in between p and g. Then the conclusion is g equals to m as a normal group times the normalizer of p. Okay, so p is very small, so probably the normalizer of p is kind of big. Okay, then we can say that G is actually m times the normalizer of p. Well, to remind you, what is a normalizer of p? Normalizer of p is just those kind of G such that, well, G inverse is equals to p. Okay, so it's like the stabilizer of p. With group action, you take the conjugate. Okay, that clear? So let's try to prove it. Again, I'm not going to introduce any application of the Frontini theory. I just want to prove the theorems as application of Sylow's group theory. Okay. So let's try to prove it. Let's see how we can do it. Okay. First, we know that, okay, M is between G and P. Okay, and then that means, okay, for any G, since it's a normal subgroup, it's still equals to M for any G in G. Okay, so which also means because you try to play with a Sylow subgroup, so you try to play with it by doing something like a conjugate, right? Then you know that this is a subgroup of G and G inverse, because you can multiply both sides by G inverse. So you get it's a subgroup. But meanwhile, it's equals to M, right? And that simply means this guy, this GPG inverse, is another Sylow P subgroup of M. Well, you may wonder, well, is that obvious? Because it's like the conjugate of a Sylow subgroup, right? Then is that obvious that this is a Sylow P subgroup of M? Why is not obvious? Why is not obvious? This guy is a Sylow P subgroup of M. We have to prove it by, okay, it's a subgroup of G and G inverse, which equals, and so it is a subgroup, and well, then you can say that since this is a subgroup, the element of this group is also P to some power, so it's also a Sylow P subgroup of M. But since this group is a conjugate of P, then why can't we say that, okay, this is, well, naturally the Sylow subgroup of M? Why can't we say that? Any idea? Any idea?
So, wait, sorry. I thought I understood it. I realized I'm confused. So we're trying to prove now the theorem by Frattini, right? Okay, and NGP is a normalizer of the group.
NGP is a normalizer of the group P.
Okay.
Define this.
And so we're basically trying to wait, what?
This is not obvious because the map may not be one-to-one and onto. May not be like one-to-one.
Well, you mean the conjugate operation? The conjugate operation is always one-to-one, right? The conjugate operation is always it's always a good action, right? But there are something to try to take us away to say that GPG inverse is actually a subgroup of M, or it's actually a Sylow P subgroup of M. What is that?
Oh wait, sorry. Can I ask a quick question? So we're trying to say that G equals to M multiplied by generalizer of
yeah,
P?
normalizer of P, yeah.
Oh, sorry. And when we're saying that, it means like G is isomorphic to their product, or
no, this just
or you
means
mean the order.
For any element of G, it can be written as one element in M times one element in this NGP. Okay, this is the meaning of this multiplication, right? So it's not it's not a direct product. It's not a product. It's not a Cartesian product. It's a group product instead of the Cartesian product. So, well, you can see that why we cannot simply say that, okay, you take the conjugate, then it must be another Sylow P subgroup. The reason is, did you see this? So this G we take to make a conjugate to make the conjugation of P is not from M. It's actually from G. It's from a bigger group. Okay? So it's from a bigger group. That means you cannot guarantee that you use an element in capital G. You do this conjugate, and then it's still a subset, or it's still a P subgroup, or it's still a subgroup of M, right? If you take any element in M and then you do the conjugation, then yes, you are right, it's still a Sylow P subgroup of M. But now you take something we don't really know, right? You take something from somewhere else, from G. Then you take the conjugation, you cannot say anything. You cannot really say anything, even whether it is a subgroup of M or not. Okay? Because this G is from G, not M. Okay? So you cannot use the Sylow second theorem.
But isn't M a normal subgroup and P is a subgroup of M? So GP G minus should also be an element in M.
Well, this is something we show, right? Why your statement is true? It's simply because we are showing that. But this is not trivial, right? So what I'm saying is, since you already know P is a Sylow P subgroup, then why can't we just say that we use a G to take the conjugation of P, then it's another Sylow P subgroup, because we know that if you take the conjugate, then you can map from one Sylow P subgroup to another Sylow P subgroup, right? But here, the trick here is you're not taking the conjugate within M. You are taking the conjugate outside M, which is why you cannot guarantee that this is still a Sylow P subgroup. You have to show it like this, okay? I'm just saying that, well, you cannot use the Sylow second to say G inverse is another Sylow P subgroup directly. You have to do this step. Okay, is that clear?
Okay.
Okay, so we know that this guy is a Sylow P subgroup, right? So that means what? That means there exists M, right? We know that from Sylows 2. There exists M such that if you take the conjugate with M of this group, it can give you back to P, okay? Right? Now you see this M is in capital M, which is why I insist you have to check, well, what kind of conjugation you are taking. This is very important. This is by Sylow 2. Okay? So, what does that mean? That means mg p mg inverse equals to P. This means mg is in the normalizer of P. That clear? So G is in M inverse NGP, which is a subset of M and GP. Since UG is arbitrary, right? G is M and GP. Because G is then a subset of M and GP, but we know that it's also, well, M and GP is a subset of G as well. So G must be equals to this group. Any question? Any question? Okay, so let's see another example. Okay, this is again an example of the application of Sylow's P group theory, Sylow's theorems, and well, it's a theoretical theorem. You can use the Sylow group theory to prove this kind of theoretical theorems. Okay, and you can see that, well, to prove this kind of abstract theorems, what you will need is you just need to play with this kind of operations, and it's not so hard. Okay, this theorem states like this. So P is a Sylow P subgroup of G. Okay, now suppose, again, you have a pretty big group in between the normalizer of P, as we defined before. It's the same thing here. It's less than H, less than G, which means H is a subgroup of G, and this normalizer of P is a subgroup of H. Okay? It's in between the normalizer and G. Then we will have H equals to NGH. H must equals to its normalizer. Okay? By the way, the reason I try to introduce these theorems is just because the proof can be seen as application of Sylow's theorems. Okay, the result of these theorems, since you are not really will see any application of this kind of theorems, you don't need to know this kind of result. Okay, you just need to know, well, in this kind of proof, how we can use the Sylow's group theory. Okay. The results are quite complicated, and it's kind of well, confusing in some sense. Okay, and if you want to make application, then the problem could be pretty hard. Of course, you can try to use them, but it's not necessary. Okay, so let's prove it. Let's prove these theorems. Now, what you have is you have a pretty big group. Then what you can tell us is, if the group is pretty big, okay, P is a Sylow P group, then the normalizer could be very big, right? It's bigger than P, because P is in the inside of the normalizer. Then, if H is even bigger, then what we can say is there is no room for H to have an even bigger normalizer. Okay, this is kind of the understanding of this theorem. Okay, so let's prove it. The proof is not so hard. It's just several lines. First, what we can show is very easily P as a Sylow P subgroup is always the normal subgroup of this normalizer of P. Right? Because well, whatever element you choose from this guy, you do the conjugate of this P, of course you will go back to P. This is the definition of the normalizer of P. Okay? And we know that it's a subgroup of H, it's a subgroup of G. So we see that P is actually a subgroup of H. Well, H is also a subgroup of G. Okay? So this means, well, P is also a Sylow P subgroup of H. Right? It has to be. It has to be, well, the maximal power of P, it has to be the order as the maximum power of P also in H, right? Because it is actually a subgroup of H. So that means for any G in your normalizer of H, okay, we have G inverse is equals to H. This is by definition. And let's try to do this conjugation, both sides of this inequality again, okay? So GP, G inverse is actually a subgroup of H, G, well, GH, G inverse, which is H. So you see this NGH is bigger than H, right? It's actually H is a subgroup with a normal subgroup of NGH. But we also see that if you use an element on this bigger group, it is actually another Sylow P subgroup of H, right? So that means there exists something. There exists some H in H just as before, right? Such that, well, since this is a Sylow P subgroup of H, then we can take a conjugacy, and then we can make this GP G inverse to go back to P, right? GP G inverse H inverse go back to P, which means HG is in NG of P. Or G is in H inverse NGP. But we know that NGP is a subset of H, right? NGP is even smaller than H. So G is in H. For every element on this normalizer of H is also an element in H. So that means the normalizer of H is a subgroup or a subset of H. That means H must be equals to the normalizer of H. Because we also know that H is also a subset of normalizer of H. Okay? So you can see that to take the conjugate of by some other element outside your original group, sometimes it can help us. If you try to do something like a group group decomposition or something. Okay? Any question? Any question about the proof of this theorem? Any question? Okay, so this other application for the Sylow P group theory or the Sylow group theory to some theoretical application. Now, just as a complement of the application to the classification of finite groups, let's see one more application, which is application of the Sylow theorems to slightly more complicated groups. Okay, slightly more complicated, which is the group of order 12. Okay, so now we want to find all kind of group of order 12. Then we want to know what kind of group could have order 12. Okay, then this is a theorem. This is this is a total classification of a group of order 12. Okay, there are 5 isomorphism classes of group of order 12. They are First one, as you can imagine, Z3 times Z4. Okay? And the second, you have Z3 times Z4, right? Of course, you also have Z4 can be something else, maybe Z2 times Z2 instead of Z4 times Z3. Okay?
Wait,
Because
can we use
times
Z2
Z2
multiplied
is
by
not a
Z4?
Z4. Hmm?
Wait,
Sorry?
but just to make sure, Z2 multiplied by Z2 is not isomorphic to Z4 because their GCD is not 1, right?
No, yeah, that's right. So Z2 times Z2 is not Z4, right? Because Z2 times Z2, it only have all the element of order 2. It's actually the Klein for group, right? But Z4 has all the element of order 4 instead of order 2. Okay, so these are two different groups. And the third one is so-called the alternating group A4. I'll tell you what is A4. Okay, I'll tell you what is alternating group in a minute. And the fourth one is, well, the so-called, you are very familiar with this guy, the dihedral group, D6, which is a group given by two elements such that x to the power 6 equals to e, y to the power 2 equals to e, x, y, well, y, x, y inverse equals to x inverse. I think I'm right. Okay. Then the last one is something similar to this dihedral group. Okay, it is a group generated by x, y, x to the power 4 equals to 1, y to the power 3 equals to e, and xy equals to y squared x. Which is like, well, somehow similar to this dihedral group, but it's fourth order element and the third order element. But still, you have this kind of relation, which is x, y, x inverse is equals to y inverse. Okay, this kind of relation. By the way, we haven't learned what is a free group, what is a generator of free groups. So, well, you are not able to show that this kind of group, they exist and the structure of this kind of group is unique. Okay, but I will just claim that this is enough. Such kind of group, they exist and the structure is unique. Okay, I'll not prove that. You can read either, well, arting or textbook if you want about the free group and the generator. Okay, so these are the 5 different classes or 5 different types of a group of order 12. It's harder than the examples we're dealing with before. Okay, so first of all, let me tell you what is this kind of group, the alternating group A4. Again, well, this part, alternating group, is something you could try to learn in the permutation group. Which is another big chapter, and if you are interested, you can try to read it in arting. Okay, arting has a lot of discussion about the permutation group. It's very important, as we've learned before. The Cauchy theorem tells us, well, every group is just a subgroup of permutation group. So as long as you know the permutation group, you know everything, right? This is, if you are interested, you can try to read yourself. So for the permutation group, we know that you may have a permutation group Sn, which is a permutation group of n letters. Okay, and we also know that if we can have a linear representation from Sn to Gl, the general linear group, and R, which is something you have done in your homework. Okay, how can we find one-to-one corresponding from this Sn, this kind of permutation group, and the matrix? How could we find that? We can find it simply by Sn acting on, say, E1, E2, until E, like a basis of Rn. Okay, and sigma, which is equals to 1, 2, until n, I1 until In. This sigma acting on, well, for instance, with this element E1 is equals to EI1. Okay, sigma acting on E2 is EI2. It's basically you interchange those, you try to do some interchange of this basis. You try to relabel them. Okay, you try to reorder them. Then this will give you a representation, a linear representation of Sn. Okay, so which means for each sigma, sigma will have a group where we have a matrix representation as something like some application of permutation. For instance, you interchange this I and j, ei and ej. That means you interchange this i's row and j's row. And you do this kind of composition or multiplication, then you got this sigma. Okay? I believe you know this when you try to learn this Gaussian elimination or this kind of echelon form of a matrix. This is like the elementary matrix. Okay, it's like every permutation can be seen as an elementary matrix or a multiplication of an elementary matrix by swapping two columns or rows. Okay, and then, well, then what we can do is we can define the sine of sigma. What is the sine of sigma? Well, you know that the determinant of this kind of swapping matrix would be, what's the determinant of this kind of matrix?
Either 1 or -1.
Either 1 or -1, right? So if you will swap the i's column and j's column, or i's row or j's row, then the determinant will be -1, right? Because you do one operation. So which means if you do that, well, odd times, if you do that some odd number of times, sigma means some odd number of times of permutation of the, well, interchange of I and j, then, well, this sine of sigma, it is sigma corresponding to a matrix A is equals to the determinant of A, which equals to +or -1. Which means if you interchange two elements, if you get the sigma by interchanging two elements even times, then the sine of sigma is 1. Otherwise, if you do that odd times, then it's -1, which is why we call it the sine of sigma, because it's +1 or -1. By the way, to show one permutation can always be written as this form. It's a little bit math. You have to show it very rigorously, but you can, well, you can see that every sigma, if you try to write it in the sense of matrix, it can always be written as some multiplication of this kind of two alternative, okay? Two index swapping, and you have a lot. And then the amount of this is the well, it can determine the sign of your sigma. Okay, then we call a permutation with the sign of this permutation equals to +1 and even permutation. Otherwise, we call it an odd permutation. You just try to count how many swapping, how many interchange you are going to do as a permutation. Okay, so you can see that one permutation is either an odd one or an even one. Okay, and meanwhile, you can see that odd permutation times odd permutation gives you an even permutation. Even times even gives you an even. Even times odd gives you an odd. Okay, so the permutation is just like the operation of your signal of a number, right? Of the sign of a number. So then you can see that if we collect all the even permutation, it forms a group. It forms a subgroup of Sn. This one, we call it the alternating group, An. And you can see that An is a subgroup of Sn. Meanwhile, it's actually a normal subgroup of Sn. Why it is normal? Why An is normal? Why it is normal?
Because even plus even is even.
Well, even not plus even, even multiplied by even, right? So if you have any element on An, right, you use sigma inverse to acting on to do the conjugate of An, right? Then for all the elements on inside of this An, sigma times that element times sigma inverse is still an even element, right? So which is why, okay, all the elements, you have an even operation, or you have an even permutation, you still get an even permutation. So that means it doesn't change the number of your An. So, well, it's a subset of An, so it's An. Okay, so it's always sigma times An times sigma inverse is always equals to An. And moreover, you can see that, well, the index of An is equals to 2. All the even elements, you can find a corresponding odd element, right? And such that this divide S into 2 parts. Well, which means An is equals to Sn divided by 2, which is n factorial divided by 2. Okay? Those are the even permutation. Of course, it's half amount of the whole permutation. Okay? Any question about this kind of permutation stuff? No?
Oh, just to make sure, what chapter of the textbook is that?
Oh, this one. This classification is actually on Artin's book. Okay? It's not on our textbook. Sorry about that. But this example is just some extra examples that I would like to provide you. You can just think this example is nowhere on the textbook. Okay? I just tell you how to do that. On Artin's book, there is one section talking about the classification of this group of order 12. Okay. Any other question? Okay, so let's try to prove it. So now what we have? We have a group of order 12. Now let's try to discuss what we can see from simply the order of the group. Okay, let's try to see. So from Sylow's theory, from Sylow's theorems, what can you see? What can you say about the subgroup of G?
Well, we can say that there should be Sylow 3 groups and Sylow 2 groups. And then we can try to compute their numbers. Like, wait. So the Sylow theorem 2 says that if we have a Sylow group 3, for example, then the number of those groups should be well, it should be equals to 1 modulus 3, right?
Yes. Okay, let's say we have a Sylow 3 group, we have a Sylow 2 group, and let's try to compute how many do we have, right? So how many Sylow 3 group we may have?
1 or 4?
1 or 4?
Yeah, that's all.
That's all, right? Because you have this number must be a factor of 12, and it mod 3 equals to 1. So it's either 1 or 4. How about the Sylow 2 group? How about this? How about Sylow 2 group?
Well, so the number of Sylow 2 groups should be odd, and it should divide 12. Yeah. So that's only 1 or 3?
Yeah, it's 1 or 3. Okay. So you either have 1 Sylow 3 group or 4 Sylow 3 group, or, well, you either have, well, 1 Sylow 2 group and or 3 Sylow 2 group. Okay. So there are 4 options that we need to discuss. Meanwhile, we know a Sylow 3 group, it must be these 3, right? However, for Sylow 2 group, we know that H2 is equals to 4. Okay, so H2 is either Z4 or the Klein 4 group, or Z2 times Z2, right? So which means we know pretty well about these 2 groups, about well, how many this kind of group we may have. So the only problem now is we have to discuss carefully. Okay. First and foremost, okay. Now, suppose what would be the easiest case? What would be the easiest case? We have K could have, you may have 1 Sylow 3 group, you may have 4 Sylow 3 group, you may have 1 Sylow 2 group, you may have 3 Sylow 2 group, right? So which means there are 4 possibilities. Which one should be the easiest
one? 1 Sylow 3 and 1 Sylow 2, because in that case, we cannot have intersection among the I mean, except for identity among groups, and so the set is Z4 cross Z3, or group cross Z3 or something like that.
Well, why is that? Why then we can get our desired result? Why is that? Do you need to check something else? Why you want it to be both 1? Why is then things becomes easier? If you only have one Sylow 3, one Sylow 2, why?
Because it would be normal.
Yes, then that means K3 is a normal subgroup of G. H2 is a normal subgroup of G, right? Then you have 2 normal subgroup. The intersection equals to trivial, right?
Oh,
then
and then their multiplication is just G.
Yes, then also, well, we know that means this multiplication of groups is, well, isomorphic to the multiplication, or the Cartesian multiplication of these 2 groups, right? But meanwhile, this one, it must equals to G. Why is that? Why this group must equals to G? Why this group must equals to G?
The order of this group is 12.
Well, why the order of this group must be 12?
Because the order is like the order of K multiply the order of H and divided the order of K intersect with H.
That's correct. We can use our counting formula, right? We've learned before. Or if you want, you can also learn that. You can also try to say that, okay, then K3 is a subgroup of this one, H2 is a subgroup of this one, so that means the order of this group must divide 3 and 4, okay? So which means it has to be at least a 12, so which is why it must be equals to G. And we know that K3 is a group of order 3. It must be cyclic. It must be Z3. And your H could be either Z4 or this Z2 times Z2. Okay? So you get the result. You get the result you want. Which seems not so hard, right? This is the easiest case.
Wait, sorry, again. I forgot how did we prove that H2 has order 4?
Well, H2 by definition, right? By definition is a Sylow 2 group. Sylow 2 group is what? Sylow 2 group, you have 12 equals to 4, which is 2 squared times 3. So Sylow 2 group simply means you must have this, well, order of this group is equals to 4. Right? This is a definition of Sylow 2 group. That okay?
Oh yeah, sure. Sorry, I forgot.
Yeah, it's okay. So we have done with the case 1. Case 1 is pretty kind of easy. Okay. Then what else can we say? What else can we do? Well, it seems that there is one situation. If this one is the easiest one, then there is one that seems to be hardest one. Right? Which is, what if you have K3 has 4 group and H2 has 3? You have 4 Sylow 3 subgroup and 3 Sylow 2 subgroup. What if this happened? What if we have a lot of groups? We have a lot of Sylow subgroup. Can we get something? Can we get something based on this condition. Hint, this is something that we've done last time. Okay? This is something we have done last time. Quite similar to that. Almost the same as what we did last time.
Should we try to find some subgroups of? Nah.
Well, if you have a lot of order three
Orbit.
Mhm.
Orbits.
Orbits,
No.
it's a little bit harder than we can imagine. Okay, I don't know whether you remember this or not, but last time we've shown that if you have a group of order 56, then it cannot be a simple group. Do you remember how we prove this? Why a group of order 56 cannot be a simple group?
Well, wait. Simple group means that you cannot divide it by like multiplication of like other groups. Do you
No,
just
a simple group simply means you do not have a proper normal subgroup.
Oh wait, oh
Seen
okay.
as some kind of finer structure of a group. If you have a finer structure, then that means you cannot divide it anymore.
Should we try to find a normal subgroup of G and show that it like equals to like say K
Yes.
or something?
Then how can we find a normal subgroup of this kind of thing, of this group of order 56? How did we do that? You can check what you have before, right? We discussed this problem last time. What's our argument? What's our argument? Or what's the idea of our argument? Yeah, of course, first, you know that you try to find the Sylow 2 group and the Sylow 7 groups. Okay? And then what you find is Sylow 2 group. You may have one Sylow 2 group, right? But you may also have 7 Sylow 2 group. Sylow 7 group. You may have one Sylow 7 group. You may also have 8 Sylow 7 group. So if either of them has one, then that means it's already a normal subgroup of your group, right? But what if you have 8 Sylow 7 group and 7 Sylow 2 group? What happened? What happened last time? Can anyone remember? What happened?
Well, should we just guess? Maybe because we have like 7 of the 8 Sylow groups, it means that and their elements should be distinct. It kind of covers all
That may not be possible.
Sylow.
Well,
You don't
but
have to
the idea is correct. The way is a little bit twisted, right? Because you don't know whether those kind of Sylow 2 group they intersect or not, right? They could have some element of order 2, some element of order 4, and some element of order 8. Both are possible. What you know is for Sylow 7 group, they don't intersect with each other, right? Because they are Sylow 7 group. They are order 7. So which means you have a lot of elements among these 8.
What? Sorry, why doesn't it intersect?
Because if you have two groups, A and B, they are of order 7. The intersect is not equals to 1. It's actually a subgroup of A, right? So, which means the order of this guy is either 1 or 7.
Oh, okay.
Subgroup, right? This is a subgroup. So, which means all this kind of group, all these 8 Sylow 7 groups provide you a lot of element of order 7. Okay? Then eventually you have a lot of things that of order 7, so you do not have enough element of order 2 or 4 or 8, which can guarantee that at least one of these Sylow groups has only 1. You cannot have both have a lot. Otherwise, you have more element than the total order of your group. Okay? This is a problem we did last time. You can check it after class if you want. So for this one, it's actually the same idea. Okay? Now you have 4 Sylow 3 group. How many elements do you have? How many distinct elements do you have among these 4 Sylow 3 group? How many?
Oh, so we can just use the same logic, like saying that intersection of those like Sylow 3 groups can only be like identity. And
Yes,
so
that's
we
right.
have 4 of them. And so if we take 4 multiplied by 3, and then we take minus 3 because we counted identity 3 times, that's how much is that? That's 9. So we have like
Yes.
only 3 elements left, so they can be order 4.
Yes, that's right. So you can see that we have, okay, this is identity, and you have one group of order 3, another group of order 3, and another group of order 3. 1, 2, 3, 4. 4 group of order 3. 1, 2, 3, and 4. Right? 4 group of order 4. They don't intersect with each other than this identity element. Then you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Totally 9 elements. 8 elements are of order 3. Okay? But on your total group, you only have 12 elements. Okay? Then 12 elements, you have 8 of order 3 and 1 identity. So you only have 3 elements left. 3 elements left. These 3 elements must of order, well, either 2 or 4, right? But then you cannot find 3 different Sylow 2 group. Because if you have 2 Sylow 2 group, then of course they must contain something different, right? So it cannot equals to 4. It can only equals to the element of the intersection can only equal 1 or 2. So which means, well, they must contain 3 elements of order either 2 or 4 plus, well, 2, at least 2 other elements of order 2 or 4. Okay, so you do not have only 3 elements of order 2 or 4. So this is a contradiction. Okay, so which means for the second case, it's also not so hard because we can exclude it, and it's impossible for us to have, well, both of them are not normal. which means there is no normal Sylow 3 subgroup. There is no normal Sylow 2 subgroup. Okay. Now, we only have 2 cases left, right? Either case 3 has 4, there are 3 Sylow subgroup and 1 Sylow 2 subgroup, or there are 3 Sylow 2 subgroup and 1 Sylow 3 subgroup. Okay, so I will pause it, and we can have a I think 15 minutes for 15 minutes break, and then we will resume at 1:21. Okay, we will finish the proof after 1:22. Or proof. Okay, let's finish this classification of group of order 12. Okay, we've discussed 2 simple cases, which one is, okay, you have 2 normal Sylow P group. Another one is you do not have any normal Sylow P groups. Okay, and these 2 situations seems to be easier. Now the harder part would be, what if you have one Sylow group is normal, another one is not? Okay, so let's say first, let's say you have, well, a lot of case 3, because case 3 seems to be easier, right? You have 4 Sylow 3 groups, okay, which let's write it as K1 3, K2 3, K3 3, K4 3. Okay, and you have only 1 Sylow 2 groups. Okay, which means this Sylow 2 groups is normal, is a normal subgroup of G. Okay. Okay. Now let's see how we can do the classification, how we can check what kind of group it is. Okay, you see, you have this group, well, this set of group, which has 4, then maybe what we want is we try to use some group to acting on it, right? If we try to use some group acting on it, maybe we can get something. Let's try to use G acting on this K1, K2, K3, and K4. This set of Sylow 3 groups. Okay, then what do we know? This is well, by conjugate. By conjugation. Okay, so which means an element in G acting on it means you take G K1 G inverse. Okay, this is something you have as an action. Then what we have is you have a action. That means you have a homomorphism from G to a group of 4 elements, right? So naturally, you have a homomorphism from G to S4. Am I right? Am I right? So now you see G now may be a subgroup of S4, right? So now what we need to say is, first, if we want to say this is actually, well, G is isomorphic to A4, which is subgroup of S4. We need to say, first, this homomorphism is an injection, right? On the other word, this phi, this action, or this representation is faithful, right? We use our fancy word. So if it is, if it is a faithful, if it is a faithful action, if it is a faithful representation, then we know that G is isomorphic to the image of G. Then we only need to find the image of G. If it is A4, we are done, right? So first, let's try to say it is, well, injection, or this phi is faithful. Why is that? Well, we want to say phi is faithful, so that means if you have some element where you have G, K1, 3, G inverse is equals to K1, 3, G, K2, 3, G inverse is equals to K2, 3, and so on. If that is true, then that means, okay, that means G equals to identity. Okay. Why is that? This seems not so easy. So, well, this just means that this G is stabilized this K1, 3, right? G stabilized K2, 3. G stabilized K3, 3. G stabilized K4, 3. Then does that mean that G must equals to identity? Well, maybe, but we need to check, okay? So in order to check that, we have to check the normalizer or the stabilizer of Ki3, right? So let's check the normalizer or stabilizer of Ki3. I equals to 1, 2, 3, and 4. Okay. So for this, well, what do we know about it? What we know about is this one. First, it has a subgroup Ki3, right? And meanwhile, we know that by our counting formula, the normalizer is equals to G divided by the orbit of, well, Ki3. Question: what is the number of the orbit of Ki3? What is the number of the orbit of Ki3? Anybody know? Anybody? What is the orbit under this action? What is Ki3? Ki3 is a Sylow 3 subgroup, right? It's a Sylow 3 subgroup of G. What is the orbit of such Sylow 3 group? What would be the orbit?
Well, do we just take this group and apply the operations from G we have in it? So that's like, wait, how many operations we have in G?
Yes, yes. Basically, how many different groups we will have, right? If we use all the elements in G to acting on K1, 3, for instance, right? How many do we have? How many different Ki3 we can get? That is the number of the orbit. Then the question is how many? What is the value of your orbit? Any idea? Any idea? Well, K13 is a Sylow P subgroup. Sylow 3 subgroup, right? So does K23. So does K33. So does K43. Right? We have 4. And what do we know about the relation between these 4 Sylow 3 groups? They conjugate to each other by the Sylow second theorems, right? So that means the action of G by the conjugation is actually transitively, right? Because we know that all of these 4 are conjugate to each other. So which means there must exist some element in G can map this one to this one, can map this one to this one, can map this one to this one, can keep it by itself. Okay, so which means, well, the orbit of this element or any other element are all the stuff. You only have one orbit of this action, right? So the number of your orbit, no matter what I is, equals to 4. It's transitively. The action is transitively. Okay? By Sylow second. So that means the stabilizer of Ki has 12/4 3 elements. But it also contains a subset Ki3. So the stabilizer is equals to Ki3. The normalizer of Ki3 is Ki3 itself. Okay, so that means phi is faithful. Because, well, all the 4 normalizer, the intersection, are just the intersection of K1, K2, K3, and K4. Of course, that's only identity element. Okay? So we get that phi is faithful. Okay? Any question? Any question? So phi is faithful. Well, that's great. So that means, okay, G is isomorphic to the image of phi. Now, the only problem now is we want to check what is the image of phi. If it is equals to A4, if it is equals to A4, then we are done, right? In this situation, we have proved that, well, this G is isomorphic to A4. It should be. So let's try to check. G has 4 Sylow 3 group. Right? So that means G has, well, 8 elements of order 3. As we mentioned before, right? It has 8 elements of order 3. What's more, these 8 elements, let's say is A1, A2, until A8, they can generate a group. What can we say about this generated group? What can we say about it? This element can generate a group. What can we say about this group? What can we say about this group? What can we say about this group?
Is there identity in it?
Well, okay, let's add identity, but identity is just like A1 to the power 0, okay? So I just ignore that. But for this one, what can you say? For this group that generated by 8 elements of order 3, what can we say about it?
It's normal?
Well, it's we don't know that, right? How can you show it is normal?
Because other elements cannot be of order 3, and if you take the conjugate, let's say G, A, I, G minus, the power, the order should
Okay.
be 3, so it is normal.
Okay. Well, that might be true, but the problem is you may have some elements on this generated group that is not of order 3. Right? You have order 3 element times another order 3 element. Then this element, if it is not a abelian group, it may not be order 3, right? It might be a problem. But, well, let me ask you, what can we say about the order of this group? What can we say about the order of this group? What can we say about the order of this group? What are the possible value of the order of this group? What are the possible value?
The divisor of 12.
Divisor of 12 and what's more?
And also 3 is a divisor of the group order.
Yes, 3 is a divisor, but there is additional thing that I forgot. We generate this group using 8 elements, right? So this group must have order greater or equal than 8. At least the 8 elements are inside of it, right? Well, the conclusion is it must equal to 12, right? Remember, we have this kind of sounds like very useless theorems we mentioned before. Sounds very stupid corollary. If you have a subgroup of order more than half of the total order of the group, then it must be everything. Well, you can see that easily here, right? So that means this 8 order 3 element can generate the whole group. Okay. Now we know that G is isomorphic to the image of V. right? Well, suppose you try to map A1 to the Sn or S4. What can we say about this VA1? What is the order of this VA1? Or what can we say about it? We map an element of order 3 to some element. What can we say about this element?
It's still order 3.
Yeah, it's still order 3. Then what else can we say? Is there anything else we can say that can help us to say this guy is actually A4? For instance, is that possible that the sine of VA1 equals to -1? Is it possible?
It's not possible because because the identity has order 1. Sine has sine 1, and -1 -1 -1 is -1. So
yes, that's right. Because the sign of a permutation is actually a homomorphism, right? So you know that this phi square, phi cube is equals to the sine of phi A1 cube. Okay? Then this is equals to the sine of E, which is 1. Then, so that means the sine of phi A1 must equals to 1. Okay? So phi AI are even elements. So that means the image of phi is a subset of A4 because all the elements here are generated by all this even order, well, all this even permutation. Okay? So that means, okay, your whole group are formed by something generated by even permutation. Now, of course, it's a subgroup or it's a subset of A4. But we know that G has 12 elements, A4 has 12 elements. So that means the image of phi is equals to A4. Or G is isomorphic to A4. Okay? Any question? Any question?
it seems that in this proof we didn't use we have one Sylow 2 group.
Well, we don't really use that exactly. But let's see. I think we didn't use that, but well, we have already said that G has 8 elements of order 3. So this means we have to have only one Sylow 2, right? So it's hiding here. It cannot have any other situations we are able to take benefit. Because you already have 8 order 3 elements. So of course, yes, of course, the rest must be only one Sylow 2 group. But you're right. We basically do not use that, well, you have only one Sylow 2 group. Because when this is true, then you of course have only one. Okay? Any other question? Okay. The last case. Case 4. Okay. Now, let's say the number of, well, Sylow 3 group is 1. The number of Sylow 2 group is 3. This is the last situation, but it's a little bit harder because we have 2 cases left, right? We need to do a lot of argument about this situation. So suppose you have, well, normal case 3 subgroup, and let's say H, you have 4, but let's say it's, well, you have 3, but let's take 1 and fix this one, okay, and see something, whether what we can say about this group, okay? Then let's try to do it like this, because we would like to take, well, because all the elements here are of order 4, right? All the elements here are of order 3. And we eventually try to prove that x, y, x inverse is equals to y inverse, this kind of condition, right? So which means we probably want, well, x is in one of them and y is in another one, the other one, right? So we try to use one group acting on another one. Let's try to do it like that. Let's try to use this H2 acting on K3. Okay, and see what happened. Well, then K3 is what? K3 is, there are 3 elements, 1, let's say y squared, 3 elements. So this action is by conjugation. Okay. So let's try to take the action. Then what we know is K3 is actually a normal subgroup, right? So that means whatever element you have, well, for any x in H2, ax, yx inverse either equals to y or equals to y squared. Because, well, x K3, x inverse is equals to K3, right? So x, y, x inverse must be one of them. It cannot be 1. It cannot be identity. Because if it is identity, then that means, okay, you must have y equals to identity. So this one either give you y or y squared. Okay. Now, let's discuss about what kind of H you have. H is a group of order 4, right? So there are 2 possibilities. First, H is Z4, okay? If H is Z4, then things are very easy, right? Then that means we can take Z, well, H is equals to the group generated by X. Then if X, Y, X inverse equals to X, well, equals to Y, then that means this G is abelian. And that means, well, we know that H is normal, which is a contradiction, right? So we must have x, y, x inverse equals to y squared. Okay? Well, that's good enough. This is actually equals to y inverse. So that means, okay, you can show that, well, this G is generated by x, y with x cubed equals, well, x to the fourth equals to e, y to the third, y to the cube equals to e, x, y, x inverse equals to y inverse.
Professor, can I ask a question? Why is
Of
this
course.
contradiction?
Why what?
Why is H is normal is a contradiction?
Because, well, we assume that there are 3 Sylow 2 groups, right? So which means, well, if you take the conjugate, you may have H1, H2, H3. It cannot be normal. If it is normal, then that's equivalent to say you only have 1 Sylow 2 groups. Okay. Any other question?
So actually, one Sylow P group and the normal group is actually an if and only if relation.
Yes, we have this corollary last time. Okay. If we want a Sylow P group to be normal, then it must be the only Sylow P group. This is if and only if. Okay. Any other question? Okay, this is when H is Z4. Okay, now what if H is not Z4, is your Klein 4 group? It's Z2 cross Z2. What happened? Well, then that's fine. We still have this K. K3 is it has 3 elements. But then on H, we have 4 elements, which are pretty simple. It's E, A, B, and AB. And H is abelian. Okay, AB are both of order 2. Okay, then we must have, okay, all this kind of thing, A acting on Y is Y either to the power 1 or 2. Let's say I1. I1 equals to 1 or 2. And B, Y, B inverse is Y to the I2. And AB, Y, AB inverse is equals to Y to the I3. Okay. That clear? And we know that I1, I2, I3 are either 1 or minus 1. Okay. So, can you say anything about I1, I2, I3? Well, can you see that this one is actually BYB inverse, right? So it's Y to the power I2. Then AY to the power I2, A inverse. That is Y to the power I2 times I1. So what you will have is I1, I2 equals to I3. They are both plus or minus 1. That clear?
Sorry, what does Y represent?
Well, Y is an element, is a generator of K3. Okay. we're trying to use our H2 to acting on, or H to acting on this K3. So which means we're trying to take the conjugate by using an element of H2 on this K3. And we try to see, okay, whether it maps y to y squared or y. Okay. Then what you find is, okay, well, I1 times I2 equals to I3. I'm sorry, it's not times. I think it's plus. Yes, it's plus. And the modular 3. Yes, modular 3. Okay. So what can we say? Well, this means if you take I1 equals to 1, I2 equals to 1, then I3 must equals to minus 1. Or if you take I1 equals to 1, I2 equals to minus 1, then I3 must equals to what? Let's say if A inverse equals to y, B inverse equals to y squared or y to the minus 1. What does that mean? That means B inverse A inverse is equals to, okay, this is y squared A inverse, right? So it's A y, A inverse, A inverse, so it's y squared, so it's y to the power minus 1. Okay. So whatever you have, you must have one of I1, I2, I3 to be plus 1, and 1 to be minus 1. If you have 2 plus 1, you have, well, this one must be minus 1. If you have 2 minus 1, this one has to be plus 1. If you have plus 1 minus 1, this one has to be minus 1. Okay? So we choose or rename the, the element corresponding to plus 1 to be, let me see my notation, to be A, okay? Corresponding to minus 1 to be B. Then what we have is A inverse equals to Y, B inverse equals to Y inverse. Okay, now this is very tedious, but it's still something I think you just need to keep on it and be careful, and then you can get it. Okay, so you have this kind of equations. This is y squared. Okay, then the magic step is here. That's trying to let x to be A times y. What we find is, well, AY, they actually commute with each other, right? AY equals to YA. Y has order 3. A has order 2, right? So we find X has order 6. That clear?
Oh, sure. But one question, but like, do I assume that at least one of A or one of B exists, and is that assumption like
Well,
necessary for our proof?
we don't have any assumption. We just take A, B, and AB, right? Then among these 3 elements, one has to give you 1, and there must be another one who gives you -1.
Oh, yeah. Okay, thank you.
Right? So which is why we must have a 1 minus 1, and then we can relabel it to be A and B, to be 1 minus 1. Okay? Then we find an element of order 6. We find an element, well, of order, of order 2, and Bx, B inverse is BAY B inverse. Okay, BAY B inverse is ABY B inverse because you have this H2 is actually an abelian group. This is A times, A times y squared. Okay, and this is equals to y squared times A, which is, well, your x is AY, which is x inverse. So we find that x to the power 6 equals to E, B squared equals to E, well, Bx B inverse equals to x inverse. So G is isomorphic to G6. Okay? Any question? Then we are done. Well, this theorem is not very easy. It's rather very complicated. Okay? However, you can see that step by step is very well, is something is always doable. If I assign this kind of problem to you, well, I hope at least that you are able to discuss. You are able to try to find how you can do this kind of argument, how you can find the relation or the generator of such groups.
Oh, by the way, all this can be on the final exam, right?
It is possible. It is possible.
No.
Well, because, well, if it is on the exam, of course, this will be a hard problem. But I think this is a problem that you are able to do. Okay? If it is over too hard, I'll give you some hint. But basically, you can see how we can find whether this group is of this type or that type, what kind of situations you will have, and so on. How could we guess that? Or how could we get that? Well, it's nothing but try and error. Okay? You do a lot of try and error, you find, okay, it must be of this form. And that's it. Any question? Any question?
So basically, for like finite length groups, it is possible to find like say 7 or 8 of the representations in the form of like multiplication of some z something groups or like the n groups, or so like what is the list of all possible things a group can be isomorphic to, like a standard list?
Well, this will be very hard problem, right? But for our course, we will just ask you to know this well-known groups, okay? And if I ask you to do a classification, of course, I will list all the possibilities for you and ask you to check. Because to find that is hard. To find that is always very hard. Okay, because well, you have to have a lot of knowledge about, well, what kind of common groups you can use as model. Okay, any other question? Okay, so we do have an extra time. So let me introduce you another example. About this example, I will not assign it in your exam because it will be something we haven't discussed systematically. So it's not fair to ask you to do anything. Okay, this is another application. Another application of group theory. Okay, so this application is not relevant. It's not very relevant to the Sylow group theory. It's simply, well, I would like to introduce this this example to you simply because our textbook is so-called abstract algebra and geometry approach, right? However, in this semester, we don't really discuss anything about the geometry because I don't want to make I want to make life easier, okay? Otherwise, you may need to do some calculations and do more about, about the matrix theory. However, I don't really want you to do that. But here, since this is almost last time I introduced something new to you, so probably I should at least give you one example to see how group can be used to understand some geometry, okay, some geometric stuff. This is something also relevant to the representation theory of a group and something in the future you may, well, if you're interested, this is something also relevant to the Lie group and Lie algebra. Although it's very, very elementary, almost does not touch anything about that, but it's kind of the first step of doing this kind of Lie group stuff, okay? By the way, in the future, after this course, if you want to learn more, there are a lot of things you could learn about abstract algebra. For instance, you can try to learn, as I said before, you can try to learn the free group theory, what is a free group and how to write a free group, how to try to write some free group that makes sense, and also the finite generated abelian group. There is a structure theory that you have done something in your homework, and also those permutation group. The permutation group is very useful, and you can use it to a lot of permutation with combinatorial problems. Okay, so if you would like to know, or if you would like to learn the combinatorial problems, combinatorial, then you will have to learn more about permutation group. Okay, and other than this kind of group stuff, you may be interested in this Galois theory. If you want to learn more about the Galois theory, then probably you will need to learn this field extension. Some of you may read this chapter in your textbook and use it in your homework. That's good, but we haven't introduced that, and I will not assume you know most of that theory, okay? But as long as you know this field extension theory, then you may try to understand what is a Galois group of a field extension. Then you may be able to prove those Galois theory, okay? Which is there is no solution, no general solution to the polynomial of order 5 or higher. And this is one. This is another part. Well, another part of this group theory or this abstract algebra would be the representation theory. Okay, representation theory, it contains a lot of things, and it will discuss a lot about, well, linear representation and also the, well, this permutation representation. Another thing is, well, the Lie group and Lie algebra. Lie group is a little bit far away from you. That is something I think you will not understand. You have to learn a lot before you learn the Lie group. But Lie algebra is something I believe you are able to learn. It's just abstract algebra plus linear algebra. So it's fine for you to learn. And well, of course, this is only the intermediate level of the abstract algebra things. Beyond that, you can learn something like number theory. Yeah, the number theory is something very interesting, and I believe most of you have learned that in your high school. But if you want to discuss it using some modern tool, you will need abstract algebra. And you may also need some Galois theory, field extension, and so on. And finite field, this kind of thing. And another thing would be, what's the other thing? Yeah, the number theory, and also very interesting and very fancy and very well advanced things. Well, algebraic geometry, okay, which is something discuss the geometry, well, the abstract structure of the intersection or the 0 point of polynomials. Okay, it's very hard. It's one of the, well, most popular area among the pure maths, and it's very, yeah, it's very hard. If you want to learn that, you may need to learn something more, like at least algebraic topology and category theory, and then maybe this algebraic geometry. And by the way, as long as you have learned the topology course, which I don't know whether it will provide here or not next year, plus this course, you will be able to learn the algebraic topology, which is you use the algebraic tool to study the topology. The most famous problem for the algebraic topology would be the Poincare conjecture, which has been proved by Perelman last, well, I think 10, maybe 20 years ago, which is a great achievement, but also leaves us even more unknown problems, well, to ask and to answer. Okay, that's very interesting. Anyway, so let me show you another application of the group theory in the sense of geometry. Okay, this is another example, say SU2C. Okay, which is the special unitary group, well, 2 by 2 special unitary group, which is all the groups, well, let's say U, all the groups U such that U times U transport with complex conjugate equals to identity. The inverse of U can be written as U transport complex conjugate. Sometimes we write this to be U star, which is the adjoint operator of U. Meanwhile, it's special something. So its determinant of U equals to 1. Okay, this is a subgroup of general linear groups, GL2C. Okay, and for a group, well, for a matrix in this group, you can see that, let's say P is in A, B, C, D. You can see that A, B, C, D are both in C. So which means at least we can see this group as a subspace of C4. Okay? But that's over too complicated. It's very hard for us to imagine what is C4. C4 has 8 dimensions, right? So maybe we need to do some simplification to see what does P satisfy, okay? So we know that P inverse can be written as determinant P inverse by the Cramer's law. This is B, D minus B and minus C and A. Okay, which is A conjugate, C conjugate, B conjugate, D conjugate. So that means A conjugate equals to D and B conjugate equals to minus. So P equals to AB minus B A conjugate. Well, A conjugate, this one, okay? And we also know that the determinant of P equals to 1, that means, okay, A's norm square plus B's norm square equals to 1, okay? So that means well, first, your P, well, your SU2C can be seen as a subset of only 2 complex numbers, or R4, right? But meanwhile, we also know that if you try to see it on R4, you will have x1 squared, let's say A equals to x1 plus I x2, B equals to x3 plus I x4. Then we have x1 squared plus x2 squared plus x3 squared plus x4 squared equals to 1. It seems to have 4 free variables, but it has 1 restriction. So which means basically it's something like a 3D stuff, right? So this thing is more or less like a sphere. It's like a sphere on R3. If it is a sphere on R3, what we will have is x squared plus y squared plus z squared equals to 1. But now you have 1 additional variable. So for this kind of thing, we call it S3, which is like a general sphere. S3 is a 3D sphere of, as a subspace or as a subset of R4. Okay, so which means we can see SU R will 2C as S3 as a sphere, 3-dimensional sphere, okay, or 3 sphere. And there is a theorem say that if you try to see this SU2C as a vector on this C4, because you only have 4 entries, right? Then you can see it as a vector on C4. Then what you can say is, well, then you may have a metric on this SU2C on C4, right? The difference, the distance between 2 elements are the corresponding element. You take the difference and then take the norm, take the square. Okay, and then take the summation, take the square root. Then what we can say is, well, it's not only somehow can be seen as S3. This is this is actually not a good notation. It can not only to be seen as S3, it's actually so-called homeomorphic to S3. Does anybody know what is homeomorphic? I think in your ODE course, Konstantinos has to mention this.
Well, now I'm kind of confused between two definitions. Is it like on and onto, right? Yeah.
Yes, there is a map, 1, 1, onto map. There's a bijection. Meanwhile, this bijection is continuous. Okay, the inverse is also continuous. Then we see these two guys are homomorphic. How can we define a function to be continuous? Of course, we can define because this is a subspace of C4. This is in a subspace of R4, right? So of course, we can use epsilon delta language to define, okay, a function from this to this is continuous. You have learned the multivariable calculus, right? And from this to this is also continuous. In that case, we say these two guys are homomorphic to each other, which somehow means you are able to see this guy, this group, as S3 in the sense of topology. Okay. Now, the thing becomes more interesting because this guy, it is somehow like a 3 sphere. Okay, it is like a sphere. It's a geometric stuff. It's a geometric object. But this is an algebraic object. So what would be the relation between this one and this one? We actually have some proposition. The first one is, what would be the conjugate class of this one on the sphere? Well, the theory just tell you, except for two special cases, special classes, the conjugacy classes in SU2C. You know, well, we have learned what is a conjugacy classes, right? It's just everything we use, we use Q or U times this element times U inverse. And then this is a conjugacy classes. And in SU2C, by the element in U2C are so-called the latitude on S3, defined as x2 squared plus x3 squared plus x4 squared equals to 1 minus c squared, or x1 equals to c. What's the meaning of latitude? Well, the latitude is you may have a sphere. What is the latitude of the sphere? It's just this kind of circle, which means you use a horizontal plane to intersect with this S2, then you get a latitude. You have a lot of latitude here, and then, well, all the latitude can be seen. This is S2, this is not S3, but in S3, all the latitudes can be seen as a conjugate classes. Okay? Which gives you an algebraic explanation or interpretation of the latitude on the sphere. Okay? The proof is actually pretty easy. You can try to prove that, well, for instance, you can try to check the characteristic equation of a matrix P. And let's say, well, then let's check the characteristic equation. What you will have is P squared minus P is equals to A bar B B bar minus, well, B minus B bar. Okay, so T minus, okay, the trace of P, A plus A bar T plus the determinant of P, which is 1. Okay, so which is this one. So you can see that x1 determine the eigenvalues of this matrix. Okay, and you gave me an x1, I'll give you an eigenvalue. Okay, and another fact is all the matrix satisfy, say A star, A times A is adjoint, is commute. This is so-called a normal matrix. Of course, the matrix on SU2 is a normal matrix. Are diagonalizable. So which means as long as you determine x1, you have determined the whole equivalent co-conjugate class of P. Okay, because as long as you determine the eigenvalues, you determine the, well, because the eigenvalue must be lambda 1 bar. So as long as you determine the eigenvalue, you have determined the conjugate class of this P. Okay, which is why this and this, they are somehow the same. Okay, this is the latitude of a sphere. And for a sphere or for globe, you do not only have the latitude, you also have so-called the longitude, right? Which is a great circle. This is the North Pole and the South Pole. Then, well, this is, if it is S2, this is the longitude, which is a vertical plane intersect with this sphere. Okay. And an interesting thing is then the longitude of SU2C are another stuff. The conjugate subgroups QTQ star, where T is all the diagonal matrix lambda times lambda bar equals to 1. All the diagonal matrix on SU2. Okay, so if you take one diagonal matrix and do the conjugacy class, you get this latitude. If you look at all this kind of conjugate things with one fixed Q of all this kind of well, diagonal matrix, then you can get this longitude. Okay. Well, the proof here, I just mentioned it. The proof, I will not prove it. The proof here is you just try to treat Q as a map. Okay, Q acting on by conjugation maps this kind of this subspace of R4. to another subspace. And you can see that if Q equals to identity, well, it is exactly a grid circle. Okay, so which means suppose W equals to say W1, W2, 0, 0. It's on this, it's on one sphere, one vertical line, one vertical plane. Then you Q equals to A, B minus B bar, A bar, acting on this W, and then you take the conjugates. It's A minus B, B bar, A. Then this equals to U, and then U1 equals to this W is actually, if you write it as a matrix, then this is Z, Z bar, right? And this is Z, Z bar. And U1 is equals to, it's linearly in W1, W2. U2 is x1 squared plus x2 squared minus x3 squared minus x4 squared omega 2, and U3 is 2x1 x4 plus x2 x3 omega 2. U4 is 2x2 x4 minus x1 x3 omega 2. Okay, which means this Q is a linear transformation, so it maps this sphere, or not sphere, it maps this vertical line, vertical space, vertical subspace, two-dimensional vertical subspace to another one, which is why it's, well, for different Q, you have different intersection, you have different grid circle, you have different longitude, okay? So I'll stop here, and this basically all I want to, well, cover for the group theory, and I hope you enjoy this abstract algebra course. And on Thursday, I will do a brief review, and then it will be your Q&A session, okay? It will be all the time for you. So before I leave, any question? Any question? Well, if you do not have any questions, just feel free to go, okay? I'm sorry I have to cancel my office hour today because I have to catch a train.
I have one question.
Of course.
So for what you just have said, like you said that the latitude was the conjugacy classes of SU to C. And the I don't know, am I understanding what right? The conjugate classes means like, if I take a point, or I take a matrix on it, and all the matrix that is similar or conjugate with this matrix can be represented as the points on the latitude. Is that right?
Yes, that's right, because every matrix is a point on R4, right? So this theorem just tells you, okay, if on R4, then this longitude, this latitude is basically all the matrix that's similar to each other. Okay?
Okay, thank you.
If you do not have any questions, feel free to go, okay? I'll have my regular office hour tomorrow and the extra office hour on Thursday.